Hi everyone, welcome back to Chem Story. Today we're going on a deep dive into one of the most useful and fascinating transformations in organic chemistry, epoxides. We'll look at how they're formed from alkenes, how different conditions can change the outcome, and what happens when that strained ring opens up, either an acid or base. We'll also break down why stereochemistry matters, when regioselectivity comes into play, and how neighboring groups can guide the reaction to one specific product. All right. Let's jump in and get started. Let's start with the basics. What exactly is epoxidation? It's a reaction where an alkene reacts with a paracid, like MCPBA, and forms a three-membered cyclic ether, which we call an epoxide. This happens through direct addition to the double bond, and since the oxygen gets added to both carbons at the same time, the reaction gives you syn addition. Now, regioselectivity? That's not something we worry about here. We're not choosing between two different carbon positions, but stereochemistry, that's important. Because the stereochemistry of the starting alkene gets carried over to the epoxide product. So the shape of what you start with really affects what you end up with. So what exactly is an epoxide? An epoxide, also called an oxirane, is a three-membered cyclic ether. And this tiny ring is under a lot of strain, about 13 kilocalories per mole, because the bond angles are forced into a very tight triangle. That ring strain makes epoxides highly reactive. They're unstable, which makes them quick to react, especially with anything that can open up the ring. Now, take a look at the structures below. You'll notice we can make a cis epoxide, but a trans epoxide doesn't really exist in small rings. Why not? Because the ring strain would be way too high. It just can't form that geometry. So whenever you see an epoxide, remember two things. It's a strained ring, and its stereochemistry tells you a lot about the alkene it came from. Now let's break down how the epoxidation reaction actually works. The key idea here is it's a concerted reaction. That means everything happens in a single step, all at once. No intermediates in between. Here's what's going on. The pi electrons from the alkene attack the electrophilic oxygen of the peroxyacid. And at the same time, the peroxyacid shifts its own electrons around. As all the bonds move together, you end up forming two products, an epoxide and a carboxylic acid. All right, now let's talk about stereochemistry, and this part is really important. Epoxidation is a stereospecific reaction. That means the stereochemistry of the product is directly determined by the stereochemistry of the starting alkene. If you start with a trans alkene, you'll get a trans epoxide. If you start with a cis alkene, you'll get a cis epoxide. It gets locked in during the reaction and shows up in the final product just as it was. Why is that? Because the oxygen is added to both carbons at the same time, and it comes in from the same face. That's a syn addition. Now, one last thing to keep in mind. Not all alkenes react at the same speed. The more substituted an alkene is, the more nucleophilic it becomes. And that means it reacts faster with the paracid. For example, a tri-substituted alkene usually reacts faster than a mono-substituted one. That's a helpful point to remember, especially when you're comparing reactivity, planning a synthesis, or trying to predict which double bond might react first in a molecule. Now let's look at another way to make an epoxide, and this one's a little different. You can actually start with a compound called a halohydrin. It has both an OH group and a halogen on neighboring carbons. Then, if you treat that halohydrin with a strong base, like sodium hydroxide, something interesting happens. The base deprotonates the alcohol, turning it into an alkoxide. That alkoxide then swings around and kicks out the leaving group, the halogen. This is a classic intramolecular SN2 reaction, and it closes the ring to form an epoxide. So even though this method doesn't involve a paracid, it's still a very reliable and efficient way to make epoxides. All right. So we've talked a lot about how to make epoxides. But what happens when you react them with water under acidic conditions? Here's the cool part. That highly strained three-membered ring can actually open up. And when it does, you get a 1,2-diol with the two OH groups added on opposite faces of the ring. That's what we call anti-addition, and it's a key feature of this type of ring-opening reaction. Just by treating an epoxide with acid and water, you get a trans-diol, which is super useful in synthesis. Now let's break down the mechanism for that acid-catalyzed ring-opening reaction. First, The acid, like H3O+, protonates the epoxide oxygen. That makes the ring even more electrophilic and sets it up for a nucleophilic attack. Then water comes in and attacks the more substituted carbon, and as that happens, the ring pops open. After a quick proton transfer, you end up with the trans 1,2 diol. The reason it ends up anti is because the attack happens from the backside, just like what we see in SN2 reactions, and that stereochemistry is preserved all the way through. We just saw how epoxides react under acidic conditions. Now let's see what happens under basic conditions. In this case, a nucleophile like hydroxide attacks the epoxide directly. No need to protonate first. The ring opens up and you get a 1,2 diol with anti-stereochemistry. Same type of product, but through a different mechanism. Now let's take a closer look at how that basic ring opening mechanism works. The hydroxide ion acts as a strong nucleophile, and it goes for the less substituted carbon of the epoxide. It attacks from the backside, just like in a classic SN2 reaction, and breaks the ring open. That gives you an alkoxide intermediate. Then water comes in and protonates that alkoxide, giving you the final product, an anti-1,2 diol. Now let's talk about something called directed epoxidation. It's a cool strategy where a nearby functional group helps control which face of the alkene the epoxidation happens on. Let's take a look at these two examples. Up top, we've got a molecule with an acetate group on the ring. When we treat it with MCPBA, we get two epoxide products, one labeled A and the other B. A is the major one at about 63%, and B is the minor one at 37%. So yeah, there's some selectivity, but nothing dramatic. Now look at the bottom example. The only thing we've changed is the acetate. We swapped it out for a hydroxyl group, and the result? Massive difference. Now we get 92% of product D and just 8% of product C. That's a huge jump in selectivity. But there's more. Not only does the ratio change, the major product actually comes from the opposite face of the alkene. So we're not just improving selectivity, we're flipping the direction of attack. Let's take a closer look at why that happens. Let's start with the first case, the one with the acetate group. There's no strong interaction between the acetate and the paracid, so the paracid can approach the double bond from either face, top, or bottom. But if you look closely at the structure, the acetate group is sticking out toward the equatorial direction. Even so, it's positioned in a way that slightly blocks the top face of the molecule. So overall, the paracid finds it just a little easier to approach from underneath. That's why we see a small preference for product A. But what if the neighboring group could interact with the reagent, maybe even guide it? Well, that's exactly what happens in our second example. Here, we've got a molecule with a hydroxyl group right next to the alkene. When we add MCPBA, something interesting happens. The OH group forms a hydrogen bond with the paracid, and that hydrogen bond pulls the reagent into a very specific position. It basically anchors the paracid right above one face of the double bond. From there, the oxygen gets delivered directly to that same face, and that's what locks in the stereochemistry of the product. That's how we end up with such high selectivity, 92% of product D and just 8% of product C. And that's the whole idea behind directed epoxidation, using a neighboring group to guide the reaction and control the outcome. So next time you see a hydroxyl group next to an alkene, think about how it might guide the reaction. It could change the whole outcome. All right, that wraps up our deep dive into epoxidation of alkenes. Thanks so much for watching, and as always, I'll see you in the next Chem Story video.